Good afternoon, everyone. I hope you guys have enjoyed previous lectures on Fibonacci or Fibonacci heaps. It's very interesting. Somebody mentioned to me that I was calling Fibonacci as I usually call Fibonacci, but it's an Italian word, and in Italian they call it Fibonacci. So whether it's Fibonacci or Fibonacci, don't worry. The major idea for lectures is to understand the underlying concepts behind these algorithms. So don't worry about terms if I pronounce something different. Um, so let me say I'm going to be consistent what I was doing. I'll call it Fibonacci. All right. So in this lecture, we're going to be seeing a different operation or algorithm, what we can do with the Fibonacci heap structure, or say Fibonacci. Um, so that's a extract min operation. So what does it mean? That we want to extract the minimum node of the Fibonacci heap. So let's say this is our favorite, a very small example of Fibonacci heap structure. I haven't shown here all the pointer connections, but assume that all these pointer connections between child nodes, left and right pointers among root lists are already there. Okay. If you are not familiar with pointers, I discussed about jungle of pointers with Fibonacci heaps in previous lectures. Nevertheless, so idea here for this algorithm is that we want to take off or remove this minimum node, which is happen to be the root node of this Fibonacci heap data structure, node number 3. So if we take off this node number 3, our heap structure gets destroyed. So that makes our life a bit difficult, how to restore the heap structure in the form of Fibonacci. This algorithm will do this job of extracting the minimum node. So as you can see, step number 1 to 10 are fairly simple. Okay, but these steps are doing that, if whatever is the minimum node, key value minimum, that node pointer, you assign it to some variable, we call it z, and that pointer, if it is not nil, means you have some elements in that heap structure. Then for each child, means each child x of this z node, what you're gonna do, because we want to take that node off from the heap. So all the children node, okay, they will go to the root list. So immediate children nodes, well, let me rephrase it. So each node is, you can think of it, say, a small tree, okay, small tree. So the root of this subtree will go in the root list of H. Okay. So 10, 45, 33 will go in the root list. Okay. And we just remove this pointer G or node 3 from this list. And rest of the job is to consolidate the final, whatever is the leftover tree you have. And also now, because this node h dot min 3 is gone, so you need to have a pointer h dot min, which will point to the new node's minimum key value root. Okay, but till we find that, for time being, what we do, we assign it to the right side, z dot right, h dot min goes to the z dot right, and that tree, resultant tree, we want to consolidate. Okay, fairly simple idea. Now the consolidate is a bit tricky operation. We will see how it is. It's not very complicated. It's just follow these steps. Okay, So what we did here, we took off this 3 and 10, 45 goes in the root list. And need to mention here all the pointers which are gonna be affected because we are moving 10 and 45 in the root list. We need to make those arrangements. And we don't have to touch any pointer structure for the child node of 10, okay, or say 33 child node. No, it's just we are playing around with the root list, right? And h dot min now point to the right node of 3, that is 16. Okay. To consolidate, now we have this tree. Okay, we want to consolidate it. Means what we want to do, we want to have a final heap, Fibonacci heap data structure in which we have all distinct roots with the all roots with a distinct degree. Now, what is the degree of a tree or of a degree of a node? We discussed it in previous lectures. You may watch that video. So it's a simple procedure. We keep on repeating these two steps. First step, find the two roots x and y in the root list, and then link these two roots with each other if these two roots happen to have the same degree. For example, 33 and 16, these two, and 10, these two, 3 happen to be the same degree, okay, and then 45 and 6 happen to be the same degree. 6 and 45 has 0 degree, and 10, 33, 16 has 1 degree each. So we want to consolidate this tree so that the resultant tree follows the Fibonacci heap data structure. Okay. Now let's talk about the algorithm for consolidation. Okay. So to consolidate, we want to keep track of pointers in an array. Okay, and the array of size dhn, and dhn is a variable which is upper bound on the degree, okay, on the degree of your Fibonacci heap structure will have. How we can calculate it? This formula, the dn is less than equal to log base phi n, is given in your textbook. Nevertheless, let's say here in our small example, we have 3 positions in this array. Starting from left, we're gonna name it as position number 0, position number 1, position number 2. All right, and this is our leftover tree when we took off its root 3. Okay. So what we do, we make an array and initially fill each position of array A with a null pointer. Okay, null pointer. Now at line number 4, for each node W in root list, means now the root list, each node W means each node 6, 10, 45, 33, 16. Okay, for all these 5 nodes, we want to execute line 5 to 14. Okay, so what we're gonna do, x equal to W means we are pointing, we are making a pointer, so let's call it, so we have x. Okay, so let's start with 16. So initially at the 5 and 6 lines, x dot W, x and W are the 16 number node, and d equal to x dot degree, which is happen to be the 1. And now we are in the while loop structure. So while a of d means a of 1 is not equal to nil. So remember, we said initially a is nil. Okay, so we are not in the loop because A is nil. So we jump over to the line number 14. Okay. AD equal to X. So we make a pointer. A1 points to 16. Okay. Now we move on to the next node. Okay. So after executing this step, very first pass of the for loop at line number 4, we are at this level. Now in the second pass, what's going to happen, that we're going to talk about number 33, right? So 33's degree is 1 and A1 is not nil now. So we are inside the while loop. So what we're going to do, we're going to have another pointer y. Okay, y is equal to A of t. Now what the idea here is that 33 and 16, only one will come, other one will become the child of the whose node is smaller. So 33 is bigger than 16. So we want to make this 33 subtree as a child of 16. Okay, so 33 becomes the child of 16. Now here, assume that we have to arrange these pointers like we discussed in the very first lecture, like that, no. That is for every, I'm not drawing all pointers here, otherwise it's going to be messy. But just assume that we have to arrange the pointers. Okay. So we at line number 12, now originally this one, A1, we make it nil and we increase the D equal to D plus 1. Okay. And then we are again in the while loop while A of t is not nil. Okay. So now A of d, so here d becomes 1 plus 1 is equal to 2. And this is nil. Okay. So we are now out of the while loop and at line number 14. Okay. And we make a pointer to 16. Good. Now we move to the node number 45. Okay. So what's going to happen at node number 45? Okay, before going to 45, we want to discuss a subroutine in between, which is called Fibo heap link, which is at line number 11. What it is doing, it is basically doing the job of what I explained, making 33 a child of 16. Okay, so it's self-evident from line number 1, 2, 3 that it is doing the linking procedure for the nodes who 16 and 33 who have the same degree. Okay, so let's move on to the next node 45. So what's going to happen at 45? So we are at line number 5. Okay, so 45's degree is 0. Okay, 0. Now we want to check whether A of d, A of 0 is nil. Here we have A of d, there is actually nothing, it's nil. Okay, so we will link basically. What we'll do, we will link A of 0 with 45. Okay. Now we move on to the next node, number 10. Same procedure, 10's degree is 1, A of 1 is nil. As we said earlier, that 0, 1, 2, these are positions in the array. Okay. So for the 10, A1 is nil, we will make a pointer. Good. Now we are at node number 6. Okay. So what's going to happen at node number 6? 6 degrees 0, and now we are at line number 7 in the inside for loop, and 7 is while condition. A of 0 is not nil, means we have to go inside the while loop. Good. Same procedure as we did earlier. We wanna compare 6 with 45, because 45 is A0 is pointing to 45. So which is smaller between 6 and 45, that will become the new root. Okay, and 45 will become a child of 6. And remember, this red color 6, it means that the node was marked. But now, since we are adjusting here in the procedure Fibo heap link, which is doing the linking procedure, we are putting mark to false. Okay, good. Now after making this link child, we are at line number 13. Increase the d equal to d plus 1, and now our d will have a1. So we are at a1. Now a1 is not nil, because a1 is pointing to 10. So now we have to decide between 6 and 10. Okay, same procedure, one will become other one's child. So 10 is bigger, 10 becomes the child node of 6. Okay, now we go back to the while loop condition, and because we incremented d equal to d plus 1 at line number 13, and we check a2. Now a2 already is pointing to 16. Same procedure we have to do. We have to check between 6 and 16. So 1 will become other one's child. So 16 is bigger than 6. 16 becomes the child of 6. Alright. Now guys, remember here, I'm assuming that you guys are following me, that we have to make necessary adjustment for pointers, as we discussed in very first lecture, that the nodes at each level will be in circularly linked list. Means 45, 10, these will be in circular linked list. 33, 28 in circular linked list. 15, we didn't touch any pointers, so original pointers will be there. Same way, whatever we didn't touch, original pointers are there, and the nodes which we modified, we have to make arrangements for those pointers. Okay, so we are done now. For every node in the root list, we finished procedure for loop up to line number 14. Now at line number 15, we want to determine what will be the minimum key value node, or the root of this Fibonacci heap. Okay, so since our example is very small, we end up having only one node in the root list, but you may have multiple nodes. So for that, the procedure line number 16 to 24 will handle that. Okay, so now let's say we are for I equal to 0 to d of hn, means we want to check each position in this array A. If it is nil, then we don't have to, we keep on moving forward. When we find a not nil position, then we insert this node which is pointed by a pointer in A position into the root list. Okay, and if we don't have any more nodes with the minimum key, it means that we found our root with the minimum key. Okay, as we can see here at line number 17, if A of I is not nil, okay, but A of I is nil here, so we are out from this if condition. But we are now in at this if condition when a of 2. So a of 2 is not nil. And now if h dot min equal to nil, which we already have, then create a root list for h containing just a of I, means we create a root list containing node number 6 for the final Fibonacci heap tree after removing the original root. So that will become our root list. Okay, we will have just only one node. Okay, all right. And we can happily call it h.min. So thank you guys. This was another lecture for Fibonacci heap data structure. I hope you guys liked it, and thank you for subscribing Lee Professor channel on YouTube. Those who haven't subscribed, please do so. Subscription helps you to get notification as soon as new lectures are posted, and we appreciate your help and support. Have a wonderful day.